Now, Cartesian coordinates are not the only coordinate system that you can work in. Oftentimes, it's more appropriate or convenient to work in curvilinear coordinates. And in this video, we'll cover how to, we'll talk about the div, grad, curl, and Laplacian operators in cylindrical coordinates. And this is covered in Greenberg chapter 16.7. You have two objectives for this video. The first is to be able to explain how the basis vectors in cylindrical coordinates change with position. And second, you'll be able to compute these differential operations in cylindrical coordinates. So let's sketch out, first of all, for reference, let's sketch out our Cartesian coordinate system. We have x, y, and z, and we would have a position point P here defined by x, y, and z, representing its location in the direction of the x-axis, its location in the direction of the y-axis, and certainly its location in the direction of the z-axis. Right, and this was z. And the base vectors were I hat. The vector base vectors are I hat, j hat, and k hat. And they remain fixed in space. They don't depend on where the position, the point P is. So this was, of course, Cartesian. And in contrast, let's look at, try to figure out where to position this picture so it's so I have room to write the other bits of information. So let's look at cylindrical coordinates. And this is covered in Greenberg's text in section 14.6. So let's sketch our same point that's going to be represented in cylindrical coordinates. And I'm projecting that point down onto the xy plane, as you can see here, as well as back to the z-axis. And the point, the same point, is going to be described in terms of cylindrical coordinates with the variables, or the position variables, r, theta, and z. So now let's talk about the base vectors in cylindrical coordinates. But before doing that, let's go back to the base vectors in Cartesian coordinates. So I hat gave the direction of increasing x. J hat gave the direction of increasing y, and k hat gave the direction of increasing z. Now the base vectors for cylindrical coordinates are E hat sub r, and that gives the direction of increasing r. E hat theta gives the direction of increasing theta, and E hat z gives the direction of increasing z. Okay, so I'm also realizing that I haven't explained to you what r, theta, and z are. So r is the length of the arm connecting in the xy plane to the projection of the point onto the plane. So this is distance r. Theta is the counterclockwise angle that r makes from the x-axis, and z is the height along the z-axis. So with those definitions of these coordinates, the direction of increasing r at point P will be outward away from the z-axis. So this is E hat r. The direction of increasing theta will be orthogonal to that. If we project that onto the xy plane, it would look like this. But up here at point P, it's E hat theta is increasing it's directed sort of into the screen of the computer and to the right. And then the direction of increasing z is again upward, E hat z. So if I were to sketch the XY plane flat onto the screen, so this is X and this is Y, and R would be here, and here's our point P right here, and so R hat, E hat sub R is in the direction of increasing R. This is theta, and E hat theta is in the direction of increasing theta. And in this picture, Z would be coming right out of the computer screen, shown by this dot with a circle around it representing the tip of an arrow pointing straight upward, straight at you. So going from Cartesian to cylindrical coordinates, we would have r is equal to the square root of x squared plus y squared, and theta is equal to, for example, the arc cosine of x over r, or the arc sine of y over r. They would be the same thing, and then z, of course, would be z. Going from cylindrical coordinates to Cartesian, we would have x is equal to r cosine theta, y is equal to r sine theta, and z again is equal to z. So this is a short summary defining cylindrical coordinates in relationship to Cartesian coordinates. I think I'm going to go ahead and end this video here and continue with our differential operations in part 2 of this video.